Hello everyone, welcome back to our NET training session. I am Muthulakshmi Kanagaraj, ASNT Level 3 in 10 methods, API, PMP and Frozio Level 3 certification holder. And it's great to continue our journey into the world of non-destructive testing. In our last session, we built a strong foundation in magnetic field theory, understanding magnetic domains, poles and different material types. Now we are going to build on that by exploring the core concept of magnetic flux and flux leakage. This is where the magic of magnetic particle testing truly happens. How we find those hidden flaws? Let's break down these concepts slide by slide to ensure everyone grasps the essentials. Let's start the session. First, let's talk about magnetic flux. You can think of magnetic flux as imaginary lines of force that represents the strength and direction of the magnetic field. These lines always seek the easiest path to travel. Magnetic flux is simply the total number of these imaginary lines of force. Flux equal to lines of magnetic force. This is the magnetic flux. There are two types of magnetic fields, circular magnetic field and longitudinal magnetic field. We will look at each one by one. First, we look circular magnetic field. Let's look at some example of circular magnetic fields. Horseshoe magnet, bent magnet ends, closed ring magnet and cracks in magnetic field. Horseshoe magnet. This is a classic example. A horseshoe magnet has distinct north and south poles. Here this is the horseshoe magnet. Here north and south poles. The magnetic flux flows from north pole to south pole through the air outside of the magnet. Through the air outside of the magnet. When you bring a ferromagnetic material near it, you will notice it's attracted only at or between these poles. Where the field is strongest, the flux lines are entering or leaving the magnet. This is a horseshoe magnet. Next we will see the bent magnet ends. If you take a magnet and bend its ends closer together, this is the closer end. So here also north pole and south pole. The pole ends become very closer and this causes the magnetic flux density to increase in that area. Magnetic flux density refers to the number of lines of flux per unit area. When the lines are packed closer, the field is very stronger. This increased density means it can attract particles across a small gap due to a strong leakage field. This is an early hint about how we detect discontinuities. Next one is closed ring magnet. This is a crucial concept. A closed ring magnet has no external poles. Because there are no external poles, the magnetic flux is entirely internal, only internal, and there is no leakage field in outside. This type of object is known as a circularly magnetized object. The magnetic field essentially runs around the circumferences of the object. Next, cracks in circular fields. Now, what happens if there is a crack in this closed ring? This crack acts like a tiny air gap in the magnetic path. This is a magnetic path. This is a tiny air gap. Remember, magnetic lines of force prefer to travel through ferromagnetic material, not the air. This air gap forces of the magnetic flux to exit the material, creating local north and south pole at the edge of this crack. When the flux exits in the material, it forms a external leakage field. This is a external leakage field. It's this leakage field then attracts magnetic particle, causing them together and form a visible indication over the crack. This is the fundamental principle for detecting discontinuities in the circularly magnetized object. So we can move the next slide. Next we will see the longitudinal magnetization. Bar magnet. Think of a bar magnet as a straightened horseshoe. It has its north and south poles primarily at its ends. The field lines travel internally between these poles within the magnet itself, and also externally in loops from north to south. Internally south to north and externally north to south. When we magnetize a long component from N to N, we are creating a longitudinal magnetic field. This is a bar magnet. Next we will see the discontinuities in longitudinal fields. Just like with circular magnetization, discontinuities like cracks, inclusions, and other flaws or problems for magnetic flux. When magnetic flux encounters a discontinuity, it disrupts the normal flow of magnetic flux. This disruption causes the flux lines to exit the material and re-enter, creating secondary poles and localized leakage field around the discontinuity. Here, exit the magnetic flux line and re-enter the material, creating secondary poles north and south. This is a localized leakage field around the discontinuity. Even fine or narrow cracks will create detectable leakage fields that are strong enough to hold the magnetic particles. This is why magnetic particle testing is so effective for surface and near surface flaws. Let's move on the next slide. Next topic is magnetic flux leakage field intensity. The strength and clarity of the indication we see depend on how strong and well defined the leakage field is. Some key factors include there are number of flux lines. It means more flux lines being forced out mean a stronger leakage field. Here more flux lines or leakage field stronger. Here more flux lines being forced out a strong leakage field. Depth of discontinuity. Deeper flaws generally produce weaker surface leakage field. Next one is width of the air gap at the surface. This is distance between north and south poles. A wider gap at the surface, like from a wide crack, might produce a more spread out field, while a tight crack creates a very concentrated sharp field. A greater intensity and curvature of the leakage field will cause more magnetic particles to be held, leading to a clearer indication. It shows the clearer indication. Next, subsurface discontinuities. Magnetic particle testing is not only for surface flaws. It can also detect the subsurface discontinuities. Example include a keyway on the far side of a component or mid-wall defects. See figure 8 and figure 9. Figure 8 represents the reverse side of the magnetic bar. Figure 8 shows the magnetized bar with the slot or keyway on its opposite side. The magnetic lines of force travel through the material. At the slot, the magnetic field is disturbed and leaks out, forming a flux leakage. This is a flux leakage. When performing a magnetic particle testing, the magnetic particles gather at the leakage, making the slot detectable even on the reverse side. Let's see the figure 9 shows a magnetized test object with an internal flaw such as void, inclusion or crack in the mid wall. This is a mid wall. At an internal discontinuity, the flux may distort, but leakage at the surface is minimal or uncertain. This is a minimal leakage. Detections depends on the strength of magnetization or size, shape, depth of the flaw. If leakage reaches the surface, magnetic particles can indicate the defect, but small or deep flaws may go undetected. Here we mention the detectability depends on proximity to the surface. The closer, the better. Size and orientation of defect, larger and optimally oriented defects are easier to find. Intensity and distribution of applied field. A strong, well-directed magnetic field is crucial. So we move on the next slide. Effect of discontinuity orientation. The golden rule of orientation for the most sensitive and effective detection, the discontinuity must be perpendicular to the magnetic flux flow. This is the very important. If flux flow in this direction means discontinuity will perpendicular. Here the discontinuity. Simple example, imagine you have a crack running east-west. To detect it best, you need to apply a magnetic field that runs north and south. This forces the lines to cut across the crack directly, maximizing the leakage. If the discontinuity is parallel to the magnetic field, there will be a minimal or no leakage field formed, making it very difficult or impossible to detect. The flux can just flow around or alongside the flaw without being forced out. So always remember perpendicular to magnetic flux flow. Discontinuity is perpendicular. So next, formation of indication. This is a final step in the magnetic particle testing process. Particle attention, the fine magnetic particles we apply in wet or dry form are attracted to this magnetic flux leakage field. They collect and build up at these locations. Under proper lighting, these accumulated particles form a visible indication. This is what the inspectors look for. In surface, here are one crack. In wet or dry, magnetic particles are spread out here. Once we apply the magnetic force, then the magnetic particles are gathered in that particular location to lead a clearer indication. The holding force on these magnetic particles depends on particles' shape. Certain shapes are more easily held. Local field intensity. Stronger leakage field hold particles more tightly. Curvature of the leakage field. A shape, tight curve holds the particles better. Next, alignment. The particles don't just randomly clump. They tend to align end to end with the leakage field, forming a clear line. A tighter leakage field results in a stronger hold on the particles, leading to a larger and clear indication. I will prepare some questions for this session. Please comment your answers in the comment box. I hope this detailed explanation gives you a clear and more comprehensive understanding of magnetic flux and flux leakage. Understanding how magnetic fields behave around flaws in this cornerstone of effective magnetic particle testing. Do you have any questions on this concept? Mention them in the comment box below. Thank you.